Hello again. In the first presentation on decision support tools for climate resilient agriculture, we looked at weather-driven models for plant and insect development, talked about why they're useful and how they work, and took a little deeper dive into degree days and chill portions specifically. In this presentation, we'll look at a typical workflow for using one of these models in practice and mention some of the websites that streamline pieces of this. I'll then get a high-level overview of some of the resources my unit, the Informatics and GIS statewide program, has been working on to make weather-driven models easier to implement using open source software, and then finish up by looking at some examples of lightweight decision support calculators we've built using these same tools. So suppose you're a grower or a farm consultant and you want to use one of these models to plan how you're going to allocate your time and resources during the season. So first you need to find a growth model, a phenology model that meets your needs. If you're interested in pest management, the UCIPM website is a good place to start. They have sifted through dozens of papers and published little summaries like this one that has all the key pieces of information. And there are similar pages for crop development, or you can go back to the original research papers and look them up there. Next, you need to know when to start counting, the biofix. Depending on the model, this might be a fixed calendar date or an observed event, such as when your trees bloom or when you see bugs start to accumulate in your traps. This could be clearly explained, or you may have to go digging for it. Next, you have to find a source of weather data. If you have your own weather station, you could use that. Many people use the CIMIS network, which is publicly funded and available and accessible through sites like the UCIPM website. Next, you have to compute degree days using the same equations that were used in the original research. If you're a whiz at Excel, you can recreate the equations on your own and feed them in your minimum and maximum daily temperatures, or you can look them up using tables like this, which are available from the UCIPM and other websites. Depending where you get your weather data, that same source may also be able to compute the degree days and give you it together with the weather data. So the last thing then is to match up the accumulated degree days that you've calculated specific for your species of interest and match them up with the phenology database. And then this is the stage where you're actually going to see when the predictions are for things like for the next generation of adults or when an action is needed. So not surprisingly, many producers don't have the bandwidth to go through this laborious process. Fortunately, cooperative extension programs have developed websites that do a lot of this work for you, including some of the ones shown here. These are great resources. They reduce the level of expertise and the level of manual steps that are required to use these weather-driven models. The designers of these sites have tried to hit the middle road, providing generic tables and generic graphs that suit a variety of purposes. They may not address your very specific needs out of the gate, but you can feed them into your own analysis or production workflow. But how do we make this easier and more flexible and adaptable so that these simple but powerful tools are easier to implement and customize for specific needs and questions? Part of the answer, we think, is to make them easier to work with for the rapidly expanding universe of open source tools and data. In the past decade, there's been exponential growth in the capabilities and popularity of open source programming languages like R and Python, as well as web development platforms. This combination has made it easier than ever to build tools for analysis and decision support. And although this is by no means niche technology. Colleges and universities are churning out tens of thousands of students every year with these skill sets, And many science programs are also including this basic training in data science. What my group has been working on are a set of resources for open source programming languages that can empower anyone with a modest amount of programming or data science experience to mix and match agroclimate models and weather data sources for different types of analysis or decision support. Now, granted, these program tools are beyond the reach of growers, but they're very much well within the reach of the vast numbers of students and data-savvy professionals who have taken a class or two in R or Python. So let me begin with a high-level overview of some of the resources we built for our users, and I should note that a link to all of these resources will be given at the end of the presentation. Degree Day is an R package that provides user-friendly, well-documented R functions to compute degree days from weather data in either tabular or raster formats. It's completely baked and is already being used in some of our online calculators. CalAdapt R is another fully developed R package that imports projected climate data from CalAdapt directly into R through the CalAdapt API. This allows you to run these same weather-driven phenology models, not just for the current season or the historical past, but also with modeled future climate data to give us an idea of how cultivar viability and pest cycles might change in the coming decades under climate change. To help the users of R or any other programming language validate that their degree day equations are actually working, because they are a little bit gnarly, we've also created a degree day computation challenge website with a reference dataset and validated answers. Anyone can go to this website to verify that their functions are working properly and get a badge for their GitHub repo or website. CA Weather is an R package under development that will build off of other packages already existing like CMIR, which queries the CIMIS network, by adding QA/QC metrics, supporting other weather data providers, including a user's own data, and forwarding the weather data in a standardized format to power all kinds of tools. Finally, the Agroclimate Community Cookbook is a GitHub site with code recipes where people can go to see examples of computing these kinds of metrics and share their own work. There's already a draft version of this up, and this will be further developed in 2023. For Python users, my colleague Shane Fire has developed a Python module with functions to compute degree days and another Python module that can import data from CalAdapt through the API. The functions in these libraries can be run in any Python environment or via a toolbox in ArcGIS Pro. So you can get CalAdapt climate data into ArcGIS Pro without knowing any programming language and without having to go to the website and download ginormous TIFF files. So what can you do with these tools? Most people start out by playing around with notebooks, which embed programming commands within something like a word processing environment. If you've never done data analysis in a programming environment like this, the best metaphor I could give would be something like a carpentry shop. With all kinds of tools, and as you gain experience with these tools, you can build almost anything. You can do chained analyses, you can bring in other data sets, you can do statistics, all manner of visualizations, and so on and so forth. It's really quite powerful and a lot of fun. Here's an example of an online decision support tool that is very user-friendly and phone-friendly. This is a precision irrigation calculator. It's not the most sophisticated example of a decision support tool, but it illustrates what you can build pretty quickly, like basically in a weekend, and published on a free website called shinyapps.io. Under the hood, it is using an R package called Shiny, which allows you to create a user interface and to program buttons that do things without knowing any HTML, which really lowers the bar. The user of the app will go to the website, enter their zip code, pick their crop and the crop stage, and the date of the last irrigation, hit run, and then the app will query the weather data from the closest CIMIS station, get the reference evapotranspiration and precipitation since the last irrigation, do some relatively simple calculations, and display the results. It's nothing fancy. You could do the same kind of thing in Excel, but it would be a lot more tedious, and it's based on solid science and is really very useful for irrigation. We talked about chill portions as a phenology model that you can also run with projected climate data. And this decision support tool will allow you to compute chill portions under climate change. It's also built with R-Shiny, and what it does is that it will compute the range of chill portions tree crop growers might expect under different climate change models and scenarios. And under the hood, it's using data from CalAdapt. Because there's multiple climate futures, these are all modeled, so we express them as probabilities. But this will tell you, for example, how many years out of 10 would you expect to have enough winter chill for your trees to bloom for a specific cultivar and a specific location. It can also tell you what would be the safe level of chill that you could expect to get 9 years out of 10 that would help you decide whether your business model might still be viable based on the cultivar that you select. The pistachio nut growth calculator, also built with Shiny, uses a regression model under the hood to forecast 3 properties of nut development: nut volume, shell hardness, and embryo length. After the user selects their location from the little map and selects their specific pistachio cultivar, the app will download the recent and forecast temperature for that location and compute the forecast properties based on the specific regression model for that cultivar. These curves are continuous, but when they start to plateau, this can tell the grower when they might want to switch from full irrigation to deficit irrigation, when the nuts might be more susceptible to pests, when they'll be likely ready to harvest, and so on. And there are other tabs with all kinds of extension resources that explain how to do these things. So to summarize, putting weather-driven models into practice takes several steps that are fairly laborious to do manually. But fortunately, cooperative extension programs and others have developed websites that eliminate many of these steps by doing the calculations for you and providing you the information in generic, multi-purpose formats that you can then continue to work with. My group is creating resources for open source data analysis environments that will lower the bar even further and allow people with beginning to intermediate level skills use these models in notebooks or decision support frameworks that are tailored to a specific use case. This QR code and URL will take you to a web page with links to all of the resources we just looked at. And in the next presentation, we'll look at some of the options for enhancing decision support tools even further. So I look forward to seeing you back for that one.